Black holes, the universe's ultimate enigma. But what if you actually fell into one? Let's strip away the sci-fi myths and dive into the real science, step by step. By the end, you'll understand why Einstein's equations predict spaghettification and why quantum physics might rewrite the rules. First, not all black holes are equal. A stellar black hole that has 5 to 50 solar masses has extreme tidal forces. A supermassive black hole, millions of solar masses like Sagittarius A at the center of our galaxy, is gentler at first. For a supermassive one, you'd cross the horizon intact. Why? Tidal force depends on mass and distance. For a stellar black hole, spaghettification happens outside the event horizon. For example, the event horizon of Sagittarius A is 12 million kilometers wide, larger than Mercury's orbit. For a small black hole, just 30 kilometers. As you near the event horizon, relativity warps reality. To distant observers, you appear frozen in time, redshifted into oblivion. But for you, time flows normally. This is the gravitational time dilation effect. Einstein's equations show time slows near massive objects. At the horizon, time stops for outsiders, but you're blissfully unaware. What's the horizon made of? Nothing. It's a mathematical boundary where escape velocity equals light speed. Once crossed, no force in the universe can pull you back. Not even light. Now, the gruesome part. Tidal forces stretch you vertically and compress you horizontally. It is known as spaghettification. Tidal force approximately equals to gravitational constant times mass of the black hole multiplied by your height, multiplied by 2 divided by the distance from the black hole's center cubed. For a stellar black hole, the distance r is small, so this force shreds you before the horizon. For a supermassive one, r is huge. You'd survive until deeper inside. This isn't sci-fi, it's how moons near planets get torn apart. But in a black hole, the forces are trillions of times stronger. As you near the singularity, space-time curvature becomes infinite. General relativity predicts a point of infinite density, but quantum mechanics forbids this. A paradox. Theorists propose alternatives. The first is quantum bounce. Singularity becomes a portal to another universe. This is loop quantum gravity. The second is fuzzballs. Strings replace the singularity, and this is from string theory. The other is firewalls. A wall of energy incinerates you, from quantum thermodynamics. But until we unify relativity and quantum theory, the singularity remains a mystery. To outsiders, you never cross the horizon. Quantum effects suggest you'd burn up at a firewall, a 2012 theory that contradicts relativity. This ties into the black hole information paradox. Does your quantum information vanish, violating quantum laws? Stephen Hawking proposed Hawking radiation. Virtual particle pairs split at the horizon, with one escaping as radiation. Over eons, this evaporates the black hole. But where does your information go? The holographic principle claims it's encoded on the horizon's surface, like a cosmic USB drive. So falling into a black hole is a one-way trip through the limits of human knowledge. But every paradox inspires discovery. Want more mind-bending science? Subscribe for deep dives into quantum foam, dark matter, and beyond. The universe is stranger than fiction. Let's explore it together. Thanks for watching. See you next time.